Continuing to work with surface area and how we can use integration to compute that. I have this curve here, y is equal to e to the x, and we're interested in x from 0 to 1. And what I want to do is take this curve and rotate it around the y-axis now. Rotate this guy around the y-axis. And what I want you to do is set up a definite integral that describes the surface area of what we get from revolving this curve around the y-axis. So pause the video and give that a try on your own. All right, assuming that you've given it a go, let's just visualize what's going on here. So when we rotate this curve, we're going to have this guy right here. We're interested in x from 0 to 1. So rotating this, it's going to look something like this. Something like this. Okay, and then we're interested in 0 to 1, so maybe we can mark that off too. Something like this. Okay, something like this, and we know that we're just going to have y here is equal to e. So this is going to be our y value right here, right there. Okay, and then what we have are these horizontal slices now. We have these horizontal slices. And what we want to do is pull one of these out and again, do what we've been doing in the last couple videos. We're going to end up figuring out what these little pieces of surface area that we want to integrate are. And let's get this. This is a circle here. This has a radius. This is all what we've seen in the last few videos. Let's get this going. And now, remember, we want to find the circumference of these horizontal slices. So this is going to be 2 pi r. And then we said we want to multiply it by what? We want to multiply it by a little piece of arc length. So a little piece of arc length. And when we do that, when we multiply these together, we get this little piece of surface area. So this right here is arc length. Right here, little piece of arc length. And now what we need to do is figure out, okay, how do we want to, what is r here and what is ds? And the main thing to notice here, we're rotating around the y-axis. So that means that r is x. R is x, okay? So r is x. So we could write this as 2 pi x, all right? And then we could also figure out ds. But one quick thing, before we get into solving for ds, what I want us to notice here, and this is an important point to make, when we're rotating about the y-axis, this r value here will always be x. Now, depending on how we want to end up integrating this, do we want to integrate this with respect to y or with respect to x? And that actually is a decision that we get to make. We could solve ds and have it in terms of dx or dy. And depending on how we want to integrate this, we want to integrate it with respect to x here, then we're fine leaving this as just x. Now, if we want to integrate this with respect to y, again, we could. Well, then if we're integrating with respect to y, we need to express x in terms of y here. So we'd have to solve y is equal to e to the x and solve that for x and have x expressed in terms of y. But again, the important point to make here, when we're revolving around the y-axis, this r value will be x. How we represent it depends on how we want to integrate. And that determines how we're going to solve for arc length, this little piece of arc length. And then similarly, when you're rotating what we've seen in the last few videos around the x-axis, r will always be y. But how you represent y will be determined on how you want to end up integrating this. And that will determine how you solve for this little piece of arc length. So that's a super important piece of information to focus on. But we said that in this video, we're going to integrate this guy with respect to x. So we're going to leave this as just x. And that means that our little piece of arc length is going to be solved for and in terms of dx. So we'll have ds is equal to the square root of dx squared plus dy squared. Okay, and then we're going to factor out dx squared out of this radical. So we'll have ds is equal to the square root of 1 plus dy over dx squared. And then we have dx out here. And lastly, all we need to do is get what dy dx is. And we're told that y is equal to e to the x. So y is equal to e to the x. And taking its derivative with respect to x, so dy dx, we love taking the derivative of e to the x because it's just e to the x. So now we can throw this guy back in and we'll have our little piece of arc length. So this is equal to the square root of 1 plus, and we said dy dx is e to the x, and then squaring that, we get e to the 2x power, and then we still have dx. All right, so this is our little piece of arc length. And now what we can do, we have all the pieces we need to construct a definite integral. We're going to sum up all of these. Maybe I can copy paste this. Just get this to look nice. There we go. There we go. Right here. Okay, this guy comes up right here. These are our little pieces of surface area. And now all we need to do is throw this into an integral. Throw some limits of integration on it, and we'll be done. Because all we're doing in this video is setting up the integral. We're not evaluating it here. So let's see here. Let's go purple. And our integrand is going to be 2 pi x, circumference of all of these horizontal slices here, and then times our little piece of arc length, which we found to be the square root of 1 plus e to the 2x power dx. And then if we're integrating with respect to x, they gave us our limits of integration in the directions. So it's going to be from 0 to 1. And this right here is our definite integral describing surface area of this curve rotated around the y-axis. And in the next video, I said we had the option to integrate this guy with respect to y. I want to show you that in the next video.